Okay, so last time what we were saying was that these two variants of Steiner tree problem on graphs, um, namely Steiner tree and Steiner forest. So in Steiner tree, we are given a set of terminals and we want all those terminals to be connected. And in Steiner forest, we are given we are given a set of pairs of terminals like A1, B1, A2, B2 till AK, BK. And what we want is A1 is connected with B1, A2 is connected with B2, and AK is connected with BK, right? So that is what Steiner forest problem is. So we said we'll design approximation algorithms for these two problems based on primal dual method, and then we started with writing an integer program for Steiner tree. Okay. So before that, let me go back to this example we had seen. I think we had made a mistake here. So in this example, if you remember, we had said that the optimal solution, the optimal Steiner forest, has cost 2. Uh, but in fact, it has cost 1 actually. So let me correct that. So it's even worse example, right? Uh, so cost 1 because you can just take this edge A1, B1, and then you can take all the top edges and all the bottom edges, and uh, everything you want to be connected will be connected. Okay. So let's move on with this integer program for Steiner tree. So we are given a graph and a set of terminals, and Steiner tree means it's a tree which connects all the vertices in the terminal set. So we said for the integer program we'll take one variable for each edge. We'll write this minimization function minimum WEXC, summation WEXC, and then we said that what constraints should we write so that the feasible solutions are exactly Steiner trees. So we said that we could write constraints corresponding to cuts. Uh, so one suggestion was so this is coming from this integer program we had seen or the linear program we had seen in the assignment 1 for spanning trees. So we are writing a similar kind of integer program. So last time we had discussed many options. So let's start with one of those options. So one option for constraints was suggested that what we can do is we can take one particular terminal, let's say T, and then look at any set of vertices such that T is inside S, right? And every other terminal, T minus T, is outside S, right? So consider all such sets of vertices, all such cuts, which basically puts one terminal on one side and all other terminals on the other side. And for all such cuts, we would like to write that summation over the cut edges is at least 1. So that means you want to take at least one edge from these cut edges delta S. So let me remind you what this delta S is. So if this is your set of vertices S and this is S bar, the outside set, then all edges which are connecting S with S bar, these are called delta S. So we are saying that you should take at least one edge from this cut edges. Okay. And we are writing these constraints for every set, for every set of vertices which splits the terminals in this fashion that one terminal is inside, some arbitrary terminal is inside, and all other terminals are outside. Okay. So that was one of the options suggested. Now my question is it good enough? Does this set of constraints ensure that a feasible solution will connect all terminals? So in fact, it turns out that these constraints are not good enough. So consider this example. Say, so we have four terminals T1, T2, T3, T4. And suppose we have a solution where T1 and T2 are connected by a path and T3 and T4 are connected by another path. Now this is not a feasible solution because we wanted that all four terminals are connected with each other. But you'll see that all these constraints are indeed satisfied by this solution. And why is that true? Because if you consider any set S which contains only one terminal, right? So it could be something like this. So for that set, you will see that there is one set, one edge which crosses this cut, right? So you could consider any set which contains only one terminal, and you will find that there is one edge crossing that cut. So in that sense, these constraints are not good enough because they were allowing a solution which should not be allowed. So we will need to add some more constraints, it seems. So in this example, maybe you can see that if you consider this set here, which contains T1 and T2 but doesn't contain T3 and T4. So for this set, there is no edge going across the cut. But if we want all four terminals to be connected, then um, there should be an edge going across this cut, right? So that kind of suggests what kind of sets we should add to this set of constraints. Yeah. So instead, let's write constraints for all sets S such that some terminals are on one side and other terminals are on the other side. So don't restrict it to only one terminal, right? So let's take an arbitrary number of terminals on one side and rest others on the other side, right? So this is the option 2. So we are considering all sets of vertices such that T, this terminal set, is split by S, meaning that T intersection S and T intersection S bar both are non-empty. So I'm just saying that you should have terminals inside S and also outside S. So any such set S is good enough for us, and we should write a constraint that for any such set S, you should take at least one cut edge. Uh, so there could be set S such that all terminals are inside but nothing outside. So I mean there are vertices outside but no terminal vertices outside. So do you think we should write any constraint for the corresponding cut set? Yeah, so we don't really need to add constraints for such sets. So if you have sets S where all terminals are present inside, then it's not necessary that you take any edges from this cut set, right? So this we don't need to include in our set of constraints, right? So let me define them as interesting cuts, okay? So basically any set of vertices S is called an interesting cut with respect to our terminal set T if both T intersection S and T intersection S bar are non-empty. Okay, so this is what we are taking as interesting cut. Now my claim is that if you write these kind of constraints for all interesting cuts, then that's good enough. Then the integral feasible solutions will exactly correspond to um, a connect. I mean, a set of uh, some subgraph which connects your all terminals. Okay, so this is my claim formally. Okay, so interesting cuts we have already defined above, right? So my claim is that suppose I get a solution which is a subset of edges. Okay, so I have a subset of edges such that for every interesting cut S, I have this property that F intersection delta S is at least 1. So meaning this set of edges F is at least taking one cut edge, right? So for every S, every interesting S, your set F is taking at least one cut edge. Then my claim is that this graph V comma F. So basically this set of edges F, if you look at this set of edges F, then all vertices in your terminal sets, in your terminal set are connected with each other. And this is what we wanted, right? We wanted all terminal vertices to be connected with each other. So basically my claim is that this kind of condition will ensure that. So do you believe this claim? So you should also verify that any Steiner tree will satisfy this constraint, right? So you take a Steiner tree which connects all your terminal vertices, then you can verify that it satisfies this property for all um, interesting cuts, right? Because see, suppose you have uh, an interesting cut where you have some terminals on one side and some other terminals on other side. If there is a Steiner tree which connects all the terminals, it has to take an edge which cuts this cut set, right? So it has to take some edge which is going across this set S. So clearly, this constraint is satisfied for every Steiner tree. My claim is that it's also true the other way, that any set of edges which satisfies this property must have must connect every terminal vertex with each other. Okay. So I will leave that as homework. So it's not very hard to verify. Just think about it that this is a good enough property. Okay.
I have a doubt.
Right. Go ahead.
So, sir,
So the question is that if I only have two terminals and I have a set S such
say
that
you have four, like suppose four terminals,
four terminals. Okay.
and like, is the question that all the four terminals need to be connected, or only that we can connect these two and
No, so I'm saying if my question was I wanted to this, right? I wanted to connect everything in the terminal set with each other. So I'm talking about the Steiner tree version.
okay.
Okay. So once you believe our above claim, then you see that uh, the integer program, if we write this integer program that xc is in 0, 1 and we want to minimize summation wexc subject to these constraints that for every interesting cut uh, this summation xc should be at least 1. Okay. So now do you think this integer program, so right now it's an integer program, do you think this integer program will give you the minimum weight Steiner tree? right? So, I mean, that's what our claim above was saying, that as
Uh,
long as we are satisfying these constraints, our
I have a
solution
doubt.
will connect. Yeah. So, yeah. So I was saying that this integer program will indeed give you the minimum weight Steiner tree. Okay. Uh, but of course, the crucial question is what happens when we convert it into an LP. Okay. So before moving on, let's consider the other variant as well. So in this variant, we had a set of terminals, and we wanted to we wanted that all terminals are connected with each other. Now let's look at this other variant, Steiner forest. So in the Steiner forest, we are given a pairs of with set of pairs. So we are given S1 T1, S2 T2, and SK TK, right? And the goal is that uh, S1 should be connected with T1, S2 should be connected with T2, and SK should be connected with TK, right? So this is the goal. Now with this, if you this is your goal, then what should be your interesting cuts? What should be the cuts for which you should write the constraints? So any suggestions? Yeah. So the suggestion is that we should look at all those sets S such that there exists I, or there is some I between 1 and k, such that uh, this ith source Si is in S, and this ith destination Ti is outside S, so is in S bar. Okay, so and this should happen for at least one terminal pair. If that is happening, then that's good enough, right? Then this S is interesting. Okay. Uh,
But that doesn't do nothing because, like, if I have S,
okay, so the question is, what if my solution is something like S1 is connected with T2 and S2 is connected with T1. So if you see, uh, so this is not a valid solution. So it should violate one of these constraints, right? And which constraint it would violate? It would violate simply uh, this constraint. So if you take S2 T1 in your set S, okay, then there is no edge which is going across this set. Okay, so this is not a good drawing, right? So
So
basically,
if you
I mean that you should take S2 and T1 in one set, uh, something like this. Then there is no edge going across this set. Uh, and this is an interesting set, right? Because S1 is on one side and T1 is on the other side, and S2 is on one side and T2 is on the other side. So we are violating this constraint.
if you add one more edge S1 T1, this will be an interesting cut. Yeah, this will satisfy this definition, but it shouldn't satisfy this.
But then everything is connected, right? If I add S1 T1, then everything is connected, so it's a valid solution.
Uh, uh, but S2 and T2 are not connected. Okay, okay,
They are
fine. Yeah,
connected via S1 T1.
yeah.
Yeah. So is it
I had a doubt.
okay? So once we have defined this interesting cuts with respect to a set of terminal pairs, basically this is my claim that uh, so for any set terminal pairs, suppose I have some set of edges such that for every interesting cut, with respect to the terminal pairs. Okay, so this interesting cut with respect to these terminal pairs, I have this property that my edge set is intersecting with this cut edges delta s, right? So it takes at least one edge from these cut edges. Then my claim is that in this subgraph v comma f, so basically using this set of edges f, si will be connected with ti for each I. Okay, so is that claim believable? Yeah. So it's true because suppose it's you can prove it by contradiction. So if suppose Si is not connected with Ti in your solution, then what you can do is just look at the uh, connected component where Si is present. Okay, and take that as your interesting cut. So clearly it's interesting because Si is inside and Ti is not inside. Okay. And then you see that there are no edges taken from these cut edges. There are no edges taken from delta S. Okay. So you are violating this constraint. So that's the proof, right? So you can think about it more. Uh, okay. So that means we can write. So basically now the point is that um, for Steiner tree and Steiner forest, we'll write the same integer program. It's just that this interesting cuts will change depending on the input. Okay, so this interesting cuts depend on the whether you are given a set of terminals or you are given a set of terminal pairs, right? Whatever. So you can define interesting cuts accordingly, and then we write these constraints only for interesting cuts, and we write them for all interesting cuts. Okay. So there are exponentially many such cuts, of course, right? So, uh, but it won't be a problem. So our number of constraints becoming exponential will not be a problem. We'll see that later on. Okay, so once we are happy with an integer program and we are convinced that the solutions for the integer program correspond to our desired solutions, and the next step is to convert it into LP. Okay, so let's convert it in LP, and the natural way to convert it in LP is so instead of this 0 1 constraint, you make it you relax it to a real numbers, right? So you make it greater than 0 and less than equal to 1. And as usual, I will ask whether this is useful or redundant. So this less than equal to 1, do you think it's useful or I can remove it?
We
So
can
because
remove it.
it's a minimization program, and let's also assume that all the edge weights are non-negative. Okay, so I think that's we have to assume. So once you assume that all edge weights are non-negative, then this minimization will ensure that you are not taking any extra edges, right? So you are only taking edges which are essential kind of. So this less than equal to 1 constraint is kind of redundant, so you can ignore it. Okay, so this is the LP we will be working with. So this is an assumption. Okay. Now, my question is, so in the integer program, we of course knew that the optimal solutions correspond to optimal Steiner trees or Steiner forests. Is it also true for this LP? So do you think the optimal solutions for this LP or the optimal value of this LP will be exactly the optimal weight of a Steiner tree, or do you think it can be different?
It will.
Yeah. So in the assignment, we have already seen that for the minimum spanning tree, we had written exactly this linear program, right? So in the spanning tree case, basically everything is an interesting cut. Every non-empty set is an interesting cut. Uh, so we had written this LP for minimum spanning tree, and we had seen in the assignment that the optimal value is not equal to the minimum weight of a spanning tree. So the optimal value is much smaller, or there was a factor of half. Uh, so that means that this LP is not exact. So it's might be true in an approximate sense, but the yeah, the optimal value is not equal. And actually, we don't expect to write an exact LP because we know that it's an NP hard problem. So if a problem is an NP hard, then and you write an exact LP for that, then you can use the LP methods to solve that problem exactly, right? So that just means that you cannot hope to write a nice LP which is exact for that problem. So does this point make sense? Yeah, so one comment is that if we know that what is the I mean how far the LP optimal can go. So like if we know that the LP optimal and the actual optimal are not very far from each other, maybe they are all the LP optimal is always uh, at least half of the actual optimal. So if we know such approximation guarantees, then it can be helpful. So it will indeed be useful when we talk about approximation algorithms. Uh, so for now, we will not go into that, but at some point we'll come to that. So for designing primal dual, it's actually important to have such a property. Uh, but we will not explicitly prove this property. So implicitly, we will prove this property that uh, the LP opt uh, and the actual opt, they are not very far from each other in the sense that LP opt is at least half of the optimal or some factor alpha. So this fact is true, but we will not explicitly prove it. Implicitly, this will be proven. We'll come to that later on. And it is indeed necessary for designing LP based algorithms. If you want to design LP based algorithms with approximation factor alpha, then this property must hold. Otherwise, that LP will not give you the desired factor. Okay. But looking at an LP, how do we know what is the approximation factor? It's not obvious. So it takes a lot of work to come up with the correct constant and so on. Okay. So for now, we are not going into that. Okay.